Great. So I'm really excited to be here and tell everybody a little bit more about Determined, which is an open source deep learning training platform. We've been building it for the last few years and recently made the decision to open source it. So basic goal of Determined is to enable deep learning engineers to train better models more quickly, to share GPU resources with their colleagues, and to collaborate, to effectively be able to spend more time on the problems they care about and less time on stuff they don't care about, which often is an unfortunate reality of deep learning today, is that in order to be successful at deep learning, you need to spend a lot of time on DevOps and other kinds of non-deep learning tasks. So in this talk, I wanted to start by motivating a little bit more, what is a deep learning training platform and why do we need such a thing? Second, I'll give a demo of the software. And third, I'll dig a little bit deeper into a few of the kind of key features and technology that we built. So why do we need better deep learning, better software infrastructure for deep learning? So I think, there's widespread excitement and enthusiasm about the potential of deep learning to really allow us to build a whole new classes of applications. So we've already seen some initial results. The smart assistants on your phone all of a sudden work a lot better. We can actually do many tasks in computer vision dramatically better than before. Self-driving cars, other kinds of applications are really powered by new advances in deep learning. But the reality is that although there are a lot of these exciting kind of theoretical advances in new kinds of neural networks and new techniques for data augmentation and so on, those kind of academic advances by themselves are not enough to be successful with deep learning. And we really think that another, in practice, a key ingredient for success with deep learning is specialized software, basically a specialized software development environment to build deep learning applications. So why is a specialized software environment? Why is that necessary for success with deep learning? I think a key reason why is that building applications powered by deep learning is just fundamentally different than building traditional software applications. So people sometimes call this, software 2.0, but basically on almost every dimension, if you're building an application powered by deep learning, the challenges you face building that application are going to be fundamentally different than the challenges you face building a traditional application. So the amount of data that you need. Traditional software, you basically need almost no data, or maybe a few tables of constants and so on. In software 2.0 and deep learning, terabytes of data is kind of very much the common case. In traditional software, building software requires some computation. Like a 4-core CPU is definitely helpful. In deep learning, almost no amount of computation is enough to be able to work as quickly with deep learning as we'd like. Even with a GPU cluster, taking days to train our model is pretty much the common case. Similarly, the kind of hardware you need to use to build deep learning applications. Traditional software, CPU has kind of been the name of the game for a long time. With deep learning, GPUs, TPUs, all kinds of custom accelerators come onto the market, both for training time and at inference. Similarly, even with this kind of new exotic hardware, the time it takes to compile your traditional application might, seconds, maybe minutes at most. In deep learning, training time and hyperparameter tuning time can easily take weeks. Similarly, even kind of the definition of what correctness looks like in a deep learning application is different, right? In traditional software, we have a logical specification where we're trying to build hard-coded rules that implement that specification correctly. Whereas with deep learning, we're following a much more kind of empirical kind of an experiment-driven workflow where we're allowing, we're running many experiments at once, exploring hypotheses, looking at data, and trying to understand whether a model architecture or whether a new set of features yields better application behavior. So if those are some of the requirements and how they're different from traditional software, how does that map into the software ecosystem for deep learning as it exists today? So the folks in the audience have probably heard of tools like TensorFlow and PyTorch, and those are great tools, particularly at small scale. So if you're a single deep learning engineer with a single GPU training a single model in a kind of experimental or research context, then a tool like PyTorch is really a perfect fit for your requirements, right? So, and that's partly because you could make a bunch of simplifying assumptions. So if you're using a single machine, you don't need to worry about, how do I manage that infrastructure or how do I share it among colleagues? If you're in the early stages of development, you probably are training a relatively small number of models. You don't need to automate things like hyperparameter tuning or distributed training. Because you're training a small number of models, keeping track of your metrics and your metadata about each model, you can do that manually. With a text file or a spreadsheet is probably sufficient. And you probably aren't thinking about production just yet, or operating that model, or enabling, maintaining that model over a sustained period of time, 6, 12, 18 months, as your data set and your models change over time. So at small scale, tools like PyTorch and TensorFlow work great. The challenge is that as you scale your team, as you scale your cluster, as you start training more models on larger data, and as those models get into production, those tools, PyTorch and TensorFlow, really don't have great solutions for a lot of the problems that arise as you start doing deep learning at scale. So all of a sudden, if you have a GPU cluster and you have multiple people on your team, how do you share that cluster among your colleagues? If you have large models and on large data sets, using multiple GPUs is crucial. How do you do distributed training? There are tools for distributed training, but they're typically hard to configure, they're fragile, they're not multi-user by default. Similarly, if you're training many different models and you're working with colleagues who are training many different models, then over a sustained period of time, you might want to understand, well, that model I trained 6, 9, 12 months ago that's been in production for 6 months, what was its behavior like when we trained it originally? What data set did we train it on? How has that data set changed over time? And how does the performance of that model now compare to how it performed when it was trained? So all of a sudden, keeping track of those metrics with a Google Sheet suddenly becomes a lot less viable. So we think that at Determined, we basically think that what's missing is essentially a infrastructure layer, what we call a deep learning training platform that basically sits between those application frameworks like TensorFlow, PyTorch, and Keras, and sits on top of the hardware resources you're using to train your deep learning models. So GPUs are basically the name of the game today, although TPUs and other kinds of custom accelerators are becoming increasingly interesting. And so importantly, we kind of view this platform as pretty focused on training models and model development. So there's a broader workflow here, which, you start with your data set and you figure out, what the important features are. You maybe do data augmentation and so on. And once you've trained a model and you have something you think works well, then you want to take that model and deploy it either to a real-time serving environment, to a mobile device, or to do batch inference. But that kind of middle piece of enabling deep learning engineers to work together, to train models, to collaborate, to share resources, to do hyperparameter tuning is really where this platform is focused. And importantly, I think it's important that any kind of deep learning platform continues to work with existing model development tools. So in our case, we support TensorFlow, PyTorch, and Keras at the moment. But the goal there really is to continue to allow model developers to use those tools that they're comfortable with, but really kind of extend them to work at scale on a cluster and with their colleagues. So some of the particular kind of technical, just give you kind of a high-level overview of the way the system works and the big components. So at the lowest level, we have a resource management layer. And you can think of that as basically a deep learning optimized GPU scheduler. And that makes it very easy for multiple users to share one GPU cluster. Also in a cloud environment, we'll manage your GPUs for you automatically. So we can provision new GPU instances as new workloads arrive in the system, and then terminate them once those instances are no longer used. On top of that resource management layer, we have built-in support for distributed training. So if you want to use multiple GPUs, that's simply a configuration setting. So you just say, when I'm training this model, by default, we'll assign one GPU to it. But if you want to use 4, 8, or 16 GPUs, you just set that configuration setting. And then our system will take care of orchestrating all the aspects of that distributed training job. Similarly, every workload in the system, we automatically track its training and validation metrics. So those metrics all get stored in a database, persisted, accessible via JSON, visualized in real time. Um, and then, another kind of key piece of functionality is hyperparameter search. So, frequently that's something that doesn't have great tool support, but but that's something that we've kind of built into the platform from the early days of working on the system. We basically felt that searching over hyperparameter space is something that can be done dramatically faster than it's typically done today. So one of my co-founders is a professor at Carnegie Mellon, and based on algorithms that his group developed in academia, we're able, by integrating hyperparameter search directly into the platform, we're able to do hyperparameter search dramatically faster than traditional methods. So that's kind of a rough overview of the different pieces of the system and how they work together. Um, oh, goodness. Speaking of wrinkles, let's see here. Start that again. Okay, let's see if I reload Chrome, if that makes it go away. Okay. Perfect. Okay, so I'll show a demo of the system in a second, but one more kind of thing I wanted to talk about is, suppose that you are an existing user of, let's say, TF Keras, and you want to start using Determined. So how do you go from that kind of single user TF Keras environment to training your models using Determined? So you do need to modify your model code. And we give you a simple API that you need to implement. These are the methods that I'm showing on the screen. Basically, you need to tell us, what is your Keras model graph? How should the system access your training data? And how should the system access your validation data set? And the reason that we ask you to tell us those things is basically that we're orchestrating your training job. So we take your model definition, we inject it into a container, and then we essentially run your training loop for you. And because we're doing that, we're able to get a bunch of really interesting functionality. So by porting your model to use our API, you get a bunch of these features that I talked about. So distributed training without changing your code, hyperparameter search, GPU scheduling, automatic fault tolerance, metrics management. But there is that upfront ask that we make of you, which is to say, take your standard Keras code and implement this kind of model API. But once you do that, then you get the kind of access to the full functionality of the product. So that's a quick overview of what Determined is and the kind of problems it is trying to solve. Now I'll switch over to giving a quick demo of the system. So this is the web UI for the system. So this is running on AWS. So this is right now there's a single agent with 8 GPUs attached to the cluster, and there's no training jobs running. And so this is the web UI. So there's kind of two main interfaces of the system. There's a command line interface that users can use to submit new experiments or examine the state of the cluster. And then there's a web interface that users can use to understand the current state of the system, what's running, dig into experiments, and understand their metrics and visualize them and so on. So you can see here, this is previous experiments that I ran on the cluster. We also have built-in support for notebooks, Jupyter notebooks, as well as tensor boards. We have one running at the moment. And you can also launch GPU-powered shells. So now let's look at what it looks like to launch a simple training job in the cluster. So we have a TF Keras model here. That trains a CNN on the Safar 10 dataset. So let's start by looking at the model definition for this example. So this is basically a standard CNN model definition. What we've done is we've ported it to use our API, as I mentioned. So that's implementing a few things like a constructor, this build model method, and a way to access the data. So, but otherwise, this is basically pretty standard TF-Keras code. So in this case, we're using the sequential API to construct the model. And we've kind of mostly just had to restructure that slightly to fit inside the, to adapt to the Determined API. So that's the first input to when we want to train a model, is the model definition itself, obviously. So the second input is a configuration file. And that tells the system what kind of workload we want to run on the cluster. So in this case, we want to train a single model, which means that we want to use fixed values for the model's hyperparameters. And in this case, we're going to train it for 50 steps, which corresponds to each step corresponds to 100 batches. So we're doing, training that model for 5,000 batches. And so just one other point on the hyperparameters. So here we've specified these kind of hyperparameter values. If we look in the model definition itself, so here's how we're basically plugging those hyperparameters into the model. So hyperparameters are totally arbitrary. They're chosen by the user. It just depends on the model that you're training, the kind of, what hyperparameters are appropriate for that model. And it's also up to you as a model developer to figure out how you want to plug those parameters into your model appropriately. And hyperparameters can control kind of any aspect of the training behavior of the model. So we can use them to do architecture search. We could also use them to do things like data augmentation. So, a hyperparameter here is kind of, we're considering that as a fairly broad definition of what a hyperparameter is. So in this case, we've said whatever the current value of the learning rate, learning decay, dropout, and so on, we're plugging that into our model definition. And then if we go back to our configuration file, we're setting those variables here. And again, right now we're using fixed variables. We'll do hyperparameter search over the hyperparameter space shortly. So now we'll use the command line interface to launch a new training workload. So that's called det, and as subcommands for the to be able to do things like launch new experiments, look at the state of the cluster, and so on. So if we want to create a new experiment, we just do det experiment create. We pass our configuration file, and then we pass the current directory that we're in. And so what happens now is the system is going to package up that model into into an archive, send that over to the cluster, and that will get scheduled on one of the GPUs in the system. So you can see that this is this new experiment running. Before we had 8 slots free, now we have 1 slot in use and 7 that are free. And then if we dig further into this workload, we can see it's already started training. And a bit of nomenclature. So we call an experiment is, or experiment consists of trials. Each trial is a single model that's being trained with a fixed set of hyperparameters. And an experiment is a collection of trials. So if you're doing hyperparameter search, you might have a single experiment with thousands of trials potentially. In this case, we're training a single model, so we just have a single experiment with a single trial. And we can see here, we can visualize the training metrics in real time, for example, look at the logs from this container as it's running. And this should finish training reasonably soon. But we can also take a look at a previous run of this model that we trained in the past. And so, we can see it took about 12 minutes to train the model, got down to a validation metric of 0.45. Great. So that's kind of the, how we launch a single workload on the cluster. But suppose that we want to do a hyperparameter search. So to do that, we use exactly the same model definition. So importantly, we don't need to modify our model code in order to run a different workload. So instead, we just use a different configuration file. So here, this is a configuration file that defines a hyperparameter search. So first, instead of the fixed values for each of the hyperparameters, we're instead using defining a range. So for each of the values, we say, okay, well, let's say, we want the dropouts to range from 0.2 to 0.5. We want to consider batch sizes between 16 and 64. We want to look at different data augmentation procedures, and different learning rates. So that defines our hyperparameter search space, right? Next, we need to configure the search itself. So we're going to be sampling points from that multidimensional space, and we need to figure out how many points do we want to sample, and how long do we want to train any one of those points. So we're using an algorithm here which is based on some work that one of my co-founders did, and that is essentially applying active learning to um, explore a large complex hyperparameter space very quickly. So essentially, what we'll be doing is we'll be training many different models and looking at the behavior of those models over time, and basically pruning model configurations that don't perform well. So what that allows us to do, and there's a lot of research kind of backing this up, I won't go into the kind of the details of the actual algorithm, but the intuition is that the system is basically adaptively allocating more training resources to the most promising hyperparameter configurations, so that we can very quickly identify points in the hyperparameter space that result in models that perform well. So that whole process of orchestrating the search, comparing different hyperparameter configurations, allocating more resources adaptively, that's handled completely by the system. The only thing we have to basically say is how many configurations in total do we want to train? And for any one of those configurations, what's the longest number what's the number of batches we want to use to train any one configuration at most? So that basically tells us, how many resources do we want to allocate to this hyperparameter search. So in this case, we're using, we're going to explore 50 configurations total and train any one of those configurations for at most 50 steps. So first of all, let's cancel that previous workload that we had running. Then let's create this new hyperparameter search workload. So again, same syntax, we just specify a different configuration file. And if we go to the interface, we can see this previous workload is being canceled and this new workload is being started. And if we look at the cluster, so because we said we want to train 50 different configurations, that's plenty of parallelism. So we can train those 50 configurations in parallel. So now all 8 slots in the cluster, all 8 GPUs in the cluster are being used. And then if we go in here, we can see that this hyperparameter search already started. This will take a little while to run. But we can see one that we've started before, which is this one here. This is a relatively small search. It only took about 11 minutes, but you can see that we've trained quite a few different configurations, each of which yielded different kind of validation behavior. And the best validation performance we were able to get down to was about 0.367. So if we then switch over to a tensor board that we have, that is looking at the training metrics and validation metrics for this experiment, we can kind of dig in here and get a bit of an intuition for what's actually happening in the search. So we can see if we zoom in here. So you can see the system has started many different configurations. And what it's doing is basically pruning configurations that are not performing well. And allocating more resources to the hyperparameter configuration that seems like it's the most promising. So again, given the way that we configured the search, we ended up training the most promising model for 5,000 batches, and the other ones for a much smaller number of batches, 300. Okay, so that's how we do a hyperparameter search. And so we can go ahead and cancel that, or let's pause it.
Neil, just a 5-minute warning.
Oh, great. Wow. Okay. Time flies. Okay. So quickly, then I'll just show how we do distributed training. So distributed training, again, same thing. We want to train one model. We want to use multiple GPUs for it. So we're going to use fixed hyperparameters because we're training a single model. And we want to say that we want to use multiple GPUs. So here we basically just say number of resources we want to use is 8 to train a single trial. So if we go here, if we look at the cluster, so actually what's happened behind the scenes, because we've had a hyperparameter search running, the system's gone ahead and allocated a bunch more GPUs from AWS automatically. As I mentioned, that's one of our capabilities. And if we want to do distributed training, we just do the same thing. Pass in a new configuration file. And we can see now immediately 8 GPUs are in use. The system's found 8 GPUs on the same machine to train this model. And we're automatically gonna orchestrate a distributed training job to use those resources. Perfect. Okay. So given the time that we have, I'll probably skip through a few of these slides a little bit. But I wanted to talk a little bit more about some of the capabilities of the system and how they're differentiated from other approaches to solving these problems. So let's start with cluster management. So if you talk to people doing deep learning today, it's often the case that people make do with relatively simple systems for managing their clusters. So it might be the case that different deep learning engineers get their own machines. So each person gets an 8 GPU machine, for example, or people use a simple calendar-based system. So everyone, Neil gets the GPUs on Monday and Bob gets GPUs on Tuesday, or they might try to use a traditional HPC queuing system. But all three of those solutions kind of result in underutilizing your GPUs. I think an improvement is to use things like Kubernetes and Mesos, which work well as kind of generic cluster schedulers or generic container orchestrators, but they're not tuned for deep learning. And as a result, the behavior you get out of those systems in terms of fault tolerance, in terms of resource management, gang scheduling, and so on, is not really well suited for deep learning workloads. In our case, we've built a GPU optimized resource manager, and that does a bunch of these, has a bunch of kind of intelligent functionality tuned for the deep learning use case. So all your jobs are automatically fault tolerant. If there's any failures, we restart them from their most recent checkpoint. We manage all your model checkpoints for you. Make it very easy to share GPUs. We can provision and terminate cloud instances automatically. So those are, I think, really helpful capabilities that really enable deep learning engineers to just focus on training models better, rather than having to worry about doing DevOps to manage GPU clusters. Similarly, if you look at how distributed training works in practice, honestly, a lot of places don't even use distributed training because it's such a pain to configure. So the result is training times are, can be days, can be weeks in some cases. So that's a very inefficient way to iterate. If you imagine every time you compiled your application took a week, it'd be very hard to make progress. So there are specialized solutions for deep learning, for distributed training of deep learning models like Horovod. And in fact, we use Horovod internally inside of Determined. But setting those kinds of systems up is really complicated and pretty difficult to do. So you have to figure out how to set up MPI and Nickel, how to enable networking and SSH between the machines. And if you want to use that in a multi-user setting, if you have, let's say 10 people on your team and a, 128 GPU cluster, using Horovod to enable that team to anyone who wants a fair share of their resources right now is a pretty complicated thing to do. So we basically made it so that you can do distributed training with no code changes that works in a multi-user aware way. And we also have a bunch of optimizations on top of Horovod that improve performance for common models. So, why does that matter? The end result is that as a team of deep learning engineers, you can apply all of your GPUs to the problems that are the most pressing. So I think I'll kind of skip through this slide just for time reasons, but I already talked a little bit about how hyperparameter search works inside the product. But yeah, so we spent the last couple of years building Determined, working with some cutting-edge deep learning teams in a few different industries, and we really feel like the product now is ready for broader adoption. So about a month ago, we released the platform under an Apache 2.0 license. So we're really excited to see what people use the platform for. Would love, if you think this is a good fit for problems that you or your team face, would love to have you try it, get your feedback. Would love to see what features you like or what other features that you'd like to see in the future. So we're on GitHub, our website's Determined.ai, and yeah, would love to see people try the product and would love to get any feedback that you might have. Okay,
Fabulous.
so
Thank you, Neil.
great.
We do have some very interested audience members who would like to ask questions.
Sure.
Srini has, I don't know if you can see the Q&A, Srini just posted an interesting question. Just for the attendees, I'm not able to unmute the individual attendees just because the audience is so big. So please go ahead and ask your questions in the Q&A, and we'll try to address them. So we're just going to take a couple minutes and probably address Srinivas's question in the Q&A.
Yeah, great. So this is a great question. It is quite long though, so I will read it and then we can talk about it. Thanks for the great talk and the nice demo. I have a long question if you don't mind. I'll post it in two parts. a conference called Scaled ML, which is dealing with some of the challenges you mentioned. The goal is, as you explained, i.e. to have something like Michelangelo, FB Learner, which anyone, even startups or smaller research labs, can use. So I also saw that there were solutions like, say, auto-scaling for Kubeflow, for visualization, logging, tracking, versioning. There's Neptune, Weights and Biases, Comet, open source solutions like MLflow. For scheduling, there's Slurm. For data processing, there's Spark. There are also end-to-end solutions like Polyaxon, Pachyderm, etc. There are also new things like Metaflow, Selden, and the space just keeps growing. So a few questions. One, how does your solution compare to these existing solutions? Two, does this work only for cloud, or do you also support on-premise? Okay, and then how are some of these things implemented? So, okay, maybe I'll start with the first two questions, and then the last question is about implementation. So first of all, how does the solution compare to these existing solutions? So I won't try to compare, kind of exhaustively compare everything compared to all the kind of options that you mentioned. Certainly, there are a bunch of this is an area where there's a bunch of interesting work being done. I think one difference between us, between Determined and other products, first of all, we're trying to build a product that is focused on training and focused on deep learning. Second, we're trying to build something that is an integrated platform for training. So something like Kubeflow is, I would say, trying to target more than just training, but it's also, I would say, more a kind of collection of building blocks that you could use to build your own ML platform. In our case, we're trying to make it, whereas like if you use Kubeflow, you have to, for example, use kubectl and write your own Kubernetes YAML files and so on. It's fairly low-level interface to the system. If you're an ML platform team and you want to build your own ML platform, something like Kubeflow might be a good starting point. Whereas we're trying to build something that is kind of more oriented for deep learning engineers to go ahead and use directly. And then compared to things like MLflow and Common ML and so on, we're trying to be a bit broader than those. So MLflow is just doing experiment tracking. We're trying to build a more complete deep learning training platform. But obviously lots of great projects out there, and I think a lot of kind of exciting ideas being developed. Second, does this work only for cloud, or do you also support on-prem? Yeah, we support both. So we actually, we're very happy to run in an on-premise environment. We also run on cloud resources on AWS and GCP, but we have plenty of our customers use us on-premise. And then in terms of implementation details, so I was curious about how much of these things are actually implemented for distributed training. So as I mentioned, for distributed training, we're using a Horovod with some optimizations. For hyperparameter search, there are implementations of algorithms like Hyperband, which are orders of magnitude faster. So in fact, yeah, so one of my co-founders is one of the inventors of Hyperband. So we're using basically an optimized version of Hyperband, but we're also integrating it into the rest of the system. So I think that is one difference, is that there are tools out there like Horovod for distributed training, or Katib for hyperparameter search, let's say. And one of the things we're trying to do that's a little different is really try to make those pieces work together really smoothly. And really trying to enable deep learning engineers to kind of get their jobs done, rather than saying, hey, here's a distributed training tool in isolation, and it's kind of up to you to figure out how to integrate that with the rest of this space, which, as you mentioned, is pretty complicated. So long question, sorry, long answer. Last question, how does Determined.ai compare to Ray? So Ray, great project, folks out of Berkeley, so go Bears. I would say at a high level, kind of just a different approach. I mean, Ray was originally focused more on reinforcement learning. Now it's kind of a bit more generic. I would say that it's more of, I would say again, a bit more of a toolkit for doing a kind of broad class of tasks, some of which you can use Ray for reinforcement learning, you can use Ray for hyperparameter tuning, whereas we're a little more focused on, building kind of an integrated system that is really kind of laser focused on training deep learning models, hyperparameter training for deep learning, and kind of putting those pieces together with a good web UI, and really trying to enable deep learning engineers to be more productive. So from that perspective, I would say we're maybe a little less generic, but a little more focused on kind of deep learning engineers and enabling them to get their jobs done.
Fabulous. Thank you so much, Neil Conway. I hope everybody will join me in thanking Neil from Determined.ai for sharing a bit about how he's reimagining this environment from the deep learning perspective to really optimize the tasks that they have to do from hyperparameter tuning and really with a laser focus there. So great. Thank you so much, Neil.
Thank you, Anya. A real pleasure to be here. And yeah, like I said, I would love folks to check out what we built, and would love any and all feedback.
And I imagine you're available if people want to contact you directly. Check out, they can contact you on your email. Great.
Absolutely, yeah. Just Neil at Determined.ai.